Physicists often like to go back 2,500 years to Democritus, who thought that everything was composed ultimately of some smallest indivisible thing called an atom, atomos in Greek. Maybe I'm not pronouncing that right. But in fact, it wasn't until 100 years ago that anyone truly believed or knew that there were atoms as such. The atom is the smallest element of, any chemical element. We now know that, however, an atom has sort of a substructure. And the substructure is a nucleus in the middle and electrons orbiting around that nucleus.
An atom is one of what were thought to be the basic units of existence. As recently as about 1910. They're about 10 billionths of a centimeter across, and going back to the Greeks, people thought that everything could be made up of a finite set of uncuttable objects called atoms. We've since learned during the 20th century, the last 100 years or so, that atoms are not the most basic things. They can be broken up into electrons, protons, and neutrons, so-called subatomic particles. And those protons and neutrons can be broken up even further into things called gluons and quarks.
The nucleus determines what type of atom you've got. However many protons and neutrons are in it determines what chemical isotope you have. Okay? So when we physicists think about atoms, we think about it definitely in terms of that structure. A very tiny nucleus with electrons going around it. To give you an idea how small the nucleus is, imagine an atom being inside the nave of a huge cathedral. Then the size of the nucleus compared to that huge cathedral would be about the size of a fly. Okay, it's really, really small compared to the whole size of the atom. Once people were convinced that there were atoms, people didn't know how the stuff inside atoms was arranged. They knew that there were electrons. In 1896, electrons were discovered by J.J. Thomson. And they thought there must be corresponding positive charge to balance the negative charge of the electrons in an atom. But they didn't know how this positive charge was distributed. So they thought it might be a raisin cake, meaning that there was some sort of fluffy stuff with positive charge, and the electrons, little dots inside it, the raisins. So they started to do experiments. And the way we do experiments today really comes out of what they were doing 100 years ago. Taking particles, shooting them at material, and seeing what comes out. So in 1910, 1911, Ernest Rutherford and his graduate students, Geiger and Marsden, that's the Geiger who made Geiger counters, did an experiment where they had a very thin gold foil and an alpha particle source. Alpha particles are the biggest, heaviest particles that come out in natural radioactivity. They, in fact, turn out to be the nucleus of a helium atom, 2 protons and 2 neutrons. But that's not important for this purpose. All they knew is that there were these things called alpha particles, and they could shoot them at things and see them bounce off. So if the atom was this raisin cake thing, the alpha particles would go through and get deflected a little bit. To their great surprise, they saw that the alpha particles sometimes would bounce straight back. Rutherford said it's like shooting a bullet at a piece of tissue paper and having it come bouncing straight back at you. Very striking discovery. And he went off and calculated it and realized that the size of the nucleus must be extremely tiny compared to the size of the atom. That was a really great discovery.
I like to think of the universe in what I call a bricks and mortar model. All right, and the bricks are the stuff of which you build your atoms and molecules and everything out of. And the bricks typically have mass. And when those are one kind of particle, like quarks and electrons. They're the bricks. And then there's another kind of particle called the force particle, generally called a boson. And they're the ones that exert force between two matter particles. And they typically don't have mass, although there are some force particles that do have mass. Mass is a very interesting thing. Mass is basically the resistance of any object to a force being applied on it. It's like inertia. It's the tendency of something to want to stay in the same place.
Okay. The great synthesis of particle physics in the 20th century was to see that we have, on the one hand, matter particles, the quarks and the leptons. And the quarks and leptons make all the ordinary matter we see around us, including the protons and neutrons and nuclei and all the chemical elements and atoms. And then on the other hand, we have force particles, the particles that we use to describe how the different forces allow the matter particles to interact with each other. Already the theorists, who are always thinking ahead of us experimentalists, had realized that you could explain the pattern of the fundamental particles like protons, neutrons, and other particles that we now call baryons in terms of combinations of then hypothetical particles that they called quarks. And indeed, once these things inside the protons and neutrons were proven to exist, it became pretty clear by around 1969 or 70 that there were indeed quarks inside protons and neutrons. In a sense, the experiment that Rutherford did to discover the nucleus was repeated again in the 1960s at SLAC, the Stanford Linear Accelerator Center near Stanford. And what they did is to take extremely high energy electrons and shoot them into solid materials, heavy materials, or even hydrogen. And look at how the electrons bounced off the protons, neutrons, and nuclei in those materials. And we're certainly looking for whether or not the protons and neutrons had some structure, even smaller things inside them, off of which the electrons could bounce.
There are 6 fundamental types of quarks, and we've been able to establish a limit on that, and it's no more than 6. And they come in pairs. The first pair, which we call the first family, are known as the up and down quark. That was named by Murray Gell-Mann, who came up with the idea of quarks in 1964. So the first family is an up and down quark. A proton is basically made up of 2 up quarks and 1 down quark. A neutron is made of 2 down quarks and 1 up quark. And all stable matter that we know about is made of those quarks and electrons, which are also part of that first family of fundamental particles. Right? Then we have 2 more families. We have the quarks, and the second family are called the strange and the charm quark, and they have short lifetimes. They decay into, they're heavier, and they have short lifetimes. They decay into other things, other light things like up and down quarks, electrons, and other things. And they have a partner that's like the electron, called a muon. That's the second family. And you'll find those in cosmic rays, for example. Most cosmic rays that make it down to the surface of the Earth are made of muons, heavy electrons.
Our Earth is constantly being bombarded from outer space by high-energy particles that we call cosmic rays. They were discovered in the 20th century using photographic emulsions, and in fact, particles were discovered using cosmic rays. That's how we discovered the positron, in fact.
Then there's a third family called it has the bottom and the top quark. And they have a corresponding or heavy cousin of the electron called the tau lepton.
Ultimately, our description of nature is just that, a description. And it's important not to confuse the description with the underlying reality for anything.
In quantum mechanics, there is a famous equation called the Schrödinger wave equation. All right? And at that time, this idea that particles had a waviness to them was becoming dominant. Einstein initially subscribed to it very much. And so Schrödinger came along and said, well, I can write down an equation that describes the behavior of an electron wave, for example. The wave form that came out of his equation, and it's a function that has a value at any point in space. All right, it might be 10 here, and it might be 1/10 over there. It's what's called it's a spatially varying function, and actually it varies in time. Then along came another German physicist named Max Born, and he reinterpreted this wave function. He said that that is really just a probability wave. All right? And if I take that wave function and I square it, that gives me the probability of finding a particle at this point at this time. The kind of wave that we're talking about here is like a crime wave. All right? In a crime wave, you walk into a certain neighborhood and you can have a function that tells you your probability of getting mugged. You're not sure you're going to get mugged as you walk through this neighborhood, but as you go through certain areas in that neighborhood, your probability gets higher. All right? So think of it as a function that tells you your probability of some occurrence. Now I'm using the probability of being mugged, but the physicists would say, well, the probability of finding a particle at this point, at this time, with maybe certain properties like certain momentum. And that's what that wave function is telling you about the system.